The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geologic record? Abstract. If an industrial civilization had existed on Earth many millions of years prior to our own era, what traces would it have left, and would they be detectable today? We summarize the likely geological fingerprint of the Anthropocene and demonstrate that while clear, it would not differ greatly in many respects from other known events in the geologic record. We then propose tests that could plausibly distinguish an industrial cause from an otherwise naturally occurring climate event. Introduction. The search for life elsewhere in the universe is a central occupation of astrobiology, and scientists have often looked to Earth analogs for extremophile bacteria, life under varying climate states, and the genesis of life itself. A subset of this search is the prospect for intelligent life, and then a further subset is the search for civilizations that have the potential to communicate with us. A common assumption is that any such civilization must have developed industry of some sort, in particular the ability to harness those industrial processes to develop radio technologies capable of sending or receiving messages. In what follows, however, we will define industrial civilization here as the ability to harness external energy sources at a global scale. One of the key questions in assessing the likelihood of finding such a civilization is an understanding of how often, given that life has arisen and that some species are intelligent, does an industrial civilization develop? Humans are the only example we know of, and our industrial civilization has lasted, so far, roughly 300 years, since, for example, the beginning of mass production methods. This is a small fraction of the time we have existed as a species, and a tiny fraction of the time that complex life has existed on Earth's land surface, around 400 million years ago. This short time period raises the obvious question as to whether this could have happened before. We term this the Silurian Hypothesis. While much idle speculation and late-night chatter has been devoted to this question, we're unaware of previous serious treatments of the problem of detectability of prior terrestrial industrial civilization in the geologic past. Given the vast increase in work surrounding exoplanets and questions related to detection of life, it is worth addressing the question more formally and in its astrobiological setting. We note also the recent work of Wright, 2017, which addressed aspects of the problem and previous attempts to assess the likelihood of solar system non-terrestrial civilizations such as Hak-Mizra and Koparapu, 2012. This paper is an attempt to remedy the gap in a way that also puts our current impact on the planet into a broader perspective. We first note the importance of the question to the well-known Drake equation. Then we address the likely geologic consequences of human industrial civilization, and then compare that fingerprint to potentially similar events in the geologic record. Finally, we address some possible research directions that might improve the constraints on this question. Chapter 1.1. Relevance to the Drake equation. The Drake equation is the well-known framework for estimating the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Drake, 1961-1965. The number of such civilizations, n, is assumed to be equal to the product of the average rate of star formation, r, in our galaxy, the fraction of formed stars that have planets, the average number of planets per star that can potentially support life, the fraction of those planets that actually develop life, the fraction of planets bearing life on which intelligent civilized life has developed, the fraction of those civilizations that have developed communications, i.e. technologies that release detectable signs into space, and the length of time over which such civilizations release detectable signals. If, over the course of a planet's existence, multiple industrial civilizations can arise over the span of time that life exists at all, the value of Fc may in fact be greater than 1. This is a particularly cogent issue in light of recent developments in astrobiology, in which the first three terms, which all involve purely astronomical observations, have now been fully determined. It's now apparent that most stars harbor families of planets. Seeger, 2013. Indeed, many of those planets will be in the star's habitable zones. Howard, 2013. Dressing and Charbonneau, 2013. These results allow the next three terms to be bracketed in a way that uses the exoplanet data to establish a constraint on the exocivilization pessimism. In Frank and Sullivan 2016, such a pessimism line was defined as the maximum biotechnological probability per habitable zone planets for humans to be the only time a technological civilization has evolved in cosmic history. Frank and Sullivan 2016 found this to be in the range of 10 to the negative 24th power to 10 to the negative 22nd power. Determination of the pessimism line emphasizes the importance of three Dirac equation terms, F, E, F, I, and Fc. Earth's history often serves as a template for discussions of possible values for these probabilities. For example, there has been considerable discussion of how many times life began on Earth during the early Archean, given the ease of abiogenesis, Patel et al. 2015, including the possibility of a shadow biosphere composed of descendants of a different origin event from the one which led to our last universal cosmic common ancestor, LUCA, Cleland and Copley, 2006. In addition, there's a long-standing debate concerning the number of times intelligence has evolved in terms of dolphins and other species, Marino, 2015. Thus, only the term Fc has been commonly accepted to have a value on Earth of strictly 1. Relevance to other solar system planets. Chapter 1.2. Consideration of previous civilizations on other system worlds has been taken on by Wright 2017 and Hack-Mizra and Koparapu 2012. We note here that abundant evidence exists of surface water in ancient Martian climates. Examples, Kiel and Hynek 2010, Arvidsson et al. 2014, and speculation that early Venus was habitable due to a dimmer sun and lower CO2 atmosphere has been supported by recent modeling studies, Wei et al. 2016. Conceivably, deep drilling operations could be carried out on either planet in future to assess their geological history. This would constrain consideration of what the fingerprint might be of life and even organized civilizations. Assessments of prior Earth events and consideration of Anthropocene markers, such as those we carry out below, will likely provide a key context for these explorations. Chapter 1.3. Limitations of the Geological Record. That this paper's title's question is worth posing is a function of the incompleteness of the geological record. For the Quaternary, the last 2.5 million years, there is widespread extant physical evidence of, for instance, climate changes, soil horizons, and archaeological evidence of non-Homo sapien culture, Denisovans, Neanderthals, etc., with occasional evidence of bipedal hominids dating back to at least 3.7 million years ago. Example, the Laetoli footprints, Leakey and Hay, 1979. The oldest extant large-scale surface is in the Negev Desert and is approximately 1.8 million years old. However, pre-Quaternary land evidence is far sparser, existing mainly in exposed sections, drilling and mining operations. In the ocean sediments, due to the recycling of ocean crust, there are only extant sediments evidence for periods that postdate the Jurassic, maybe 170 million years ago. The fraction of life that gets fossilized is always extremely small and varies widely as a function of time, habitat, and degrees of soft tissues versus hard shells or bones. Fossilization rates are very low in tropical forested environments, but are higher in arid environments and fluvial systems. As an example, for all the dinosaurs that ever lived, there are only a few thousand near-complete specimens, or equivalently only a handful of individual animals across thousands of taxa per 100,000 years. Given the rate of new discovery of taxa of this age, it is clear that species as short-lived as Homo sapiens, so far, might not be represented in the existing fossil record at all. The likelihood of objects surviving and being discovered is similarly unlikely. Zaleswich, 2009, speculates about preservation of objects or their forms, but the current area of urbanization is less than 1% of the Earth's surface. Schneider et al., 2009. And exposed sections and drilling sites for pre-quaternary surfaces are orders of magnitude less as fractions of the original surface. Note that even for early human technology, complex objects are very rarely found. For instance, the Antikythera mechanism around 205 BC is a unique object until the Renaissance. Despite impressive recent gains in the ability to detect the wider impacts of civilization on landscapes and ecosystems, we conclude that for potential civilizations older than about 4 million years ago, the chances of finding direct evidence of their existence via objects or fossilized examples of their population is small. We note, however, that one might ask the indirect question related to antecedents in the fossil record, indicating species that might lead downstream to the evolution of later civilization-building species. Such arguments for or against the Silurian hypothesis would rest on evidence concerning highly social behavior or high intelligence based on brain size. The claim would then be that there are other species in the fossil record which could or could not have evolved into civilization builders. In this paper, however, we focus on physico-chemical tracers for previous industrial civilizations. In this way, there's an opportunity to widen the search to tracers that are more widespread, even though they may be subject to more varied interpretations. Chapter 1.4. The scope of this paper. We will restrict the scope of this paper to geochemical constraints on the existence of pre-quaternary industrial civilizations that may have existed since the rise of complex life on land. This rules out societies that might have been highly organized and potentially sophisticated, but that did not develop industry and probably any purely ocean-based life forms. The focus is thus on the period between the emergence of complex life on land in the Denisovan, perhaps Devonian, perhaps 400 million years ago, in the Paleozoic era, and the mid-Pliocene, around 4 million years ago. Chapter 2. The Geologic Footprint of the Anthropocene. While an official declaration of the Anthropocene as a unique geological era is still pending, Crutzen 2002, Zalesewicz et al. 2017, it's already clear that our human efforts will impact the geologic record being laid down today. Walters et al. 2014. Some of the discussions on specific boundary that will define this new period is not relevant for our purposes because the markers proposed, ice core, gas concentrations, short half-lived radioactivity, the Columbian exchange, examples Lewis and Maslin 2015, Hamilton 2016, are not going to be geologically stable or distinguishable on multi-million year timescales. However, there are multiple changes that have already occurred that will persist. We discussed a number of these below. There's an interesting paradox in considering the anthropogenic footprint on a geological timescale. The longer human civilization lasts, the larger the signal one would expect in the record. However, the longer a civilization lasts, the more sustainable its practices would need to have become in order to survive. The more sustainable a society, example in energy generation, manufacturing, or agriculture, the smaller the footprint on the rest of the planet. But the smaller the footprint, the less of a signal will be embedded in the geological record. Thus, the footprint of civilization might be self-limiting on a relatively short time scale. To avoid speculating about the ultimate fate of humanity, we will consider impacts that are already clear or that are foreseeable under plausible trajectories for the next century. Examples: Kohler 2016, Narazenko et al. 2015. We note that effective sedimentation rates in ocean sediment for cores with multi-million-year-old sediment are on the order of a few centimeters per 1,000 years at best. And while the degree of bioturbation may smear a short-period signal, the Anthropocene will likely only appear as a section a few centimeters thick and appear almost instantaneously in the record. Chapter 2.1 Stable Isotope Anomalies of Carbon, Oxygen, Hydrogen, and Nitrogen. Since the mid-18th century, humans have released over 0.5 trillion tons of fossil carbon via the burning of coal, oil, and natural gas, at a rate orders of magnitude faster than natural long-term sources or sinks. In addition, there have been widespread deforestation and addition of carbon dioxide into the air via biomass burning. All of this carbon is biological in origin and is thus depleted in the C13 compared to the much larger pool of inorganic carbon, Reveley and Seuss, 1957. Thus, the ratio of C13 to C12 in the atmosphere, ocean, and soils is decreasing, an impact known as the Seuss effect. Key et al., 1992. With a current change of around -1 delta 13C since the pre-industrial Boom et al. 2002, Ide et al. 2017, in the surface ocean and atmosphere. As a function of the increase of fossil carbon into the system, augmented by black carbon changes, other non-CO2 trace greenhouse gases like NO2, CH4, and chlorofluorocarbons. Global industrialization has been accompanied by a warming of about 1 degree centigrade so far since the mid-19th century. Due to the temperature-related fractionation in the formation of carbonates, and strong correlation in the extratropics between temperature between 0.4 and 0.7 per 0 degrees centigrade, and roughly 8 times as sensitive for deuterium isotopes related to hydrogen, we expect this temperature rise to be detectable in surface ocean carbonates, notably foraminifera, organic biomarkers, cave records, stalactites, lake ostracods, and high-latitude ice cores. Through only the first 2 of these will be retrievable in the timescales considered here. The combustion of fossil fuel, the invention of Haber-Bosch process, the large-scale applications of nitrogenous fertilizers, and the enhanced nitrogen fixation associated with cultivated plants have caused a profound impact on nitrogen cycling, such that anomalies are already detectable in settlements remote from civilizations. Chapter 2.2 Sedimentological Records. There are multiple causes of a greatly increased sediment flow in rivers, and therefore in deposition in coastal environments. The advent of agriculture and associated deforestation have led to large increases in soil erosion. Furthermore, canalization of rivers, such as the Mississippi, have led to much greater oceanic deposition of sediments than otherwise would have occurred. This tendency is mitigated somewhat by concurrent increases in river dams, which reduce sediment flow downstream. Additionally, increasing temperatures and atmospheric water vapor content have led to greater intensity of precipitation, which on its own would also lead to greater erosion, at least regionally. Coastal erosion is also on the increase as a function of rising sea level, and in polar region is being enhanced by reduction of sea ice and thawing permafrost. In addition to changes in the flux of sediment from land to ocean, the composition of the sediments will also change. due to increasing dissolution of CO2 in the ocean as a function of anthropogenic CO2 emissions, the upper ocean is acidifying, a 26% increase in H+, or 0.1 pH decrease since the 19th century. That's Orr et al. 2005. This will lead to an increase in calcium carbonate dissolution within the sediment that will last until the ocean can neutralize the increase. There will also be important changes in mineralogy. Increases in continental weathering are also likely to change ratios of strontium and osmium. As discussed above, nitrogen load in rivers is increasing as a function of agricultural practices. This in turn is leading to more microbial activity in the coastal ocean, which can deplete dissolved oxygen in the water column. And recent syntheses suggest a global decline already of about 2%. This in turn is leading to an expansion of the oxygen minimum zones, greater ocean anoxia, and the creation of so-called dead zones. Sediment within these areas will thus have greater organic content and less bioturbation. The ultimate extent of these dead zones is unknown. Furthermore, anthropogenic fluxes of lead, chromium, antimony, rhenium, platinum group metals, rare earth, and gold are now much larger than their natural sources, implying that there will be a spike in fluxes in those metals in river outflow, and hence higher concentrations in coastal sediments. Chapter 2.3 Faunal Radiation and Extinction. The last few centuries have seen significant changes in the abundance and spread of small animals, particularly rats, mice, and cats, that are associated with human exploration and biotic exchanges. Isolated populations almost everywhere have now been superseded in many respects by these invasive species. The fossil record will likely indicate a large faunal radiation of these indicator species at this point. Concurrently, many other species have already or are likely to become extinct, and their disappearance from the fossil record will be noticeable. Given the perspective from many millions of years ahead, large mammal extinctions that occurred at the end of the last ice age were also associated with the onset of the Anthropocene. Chapter 2.4 Non-naturally occurring synthetics. There are many chemicals that have been or were manufactured industrially that for various reasons can spread and persist in the environment for a long time. Most notably, persistent organic pollutants, POPs, organic molecules that are resistant to degradation by chemical, photochemical, or biological processes, are known to have spread across the world, even to otherwise pristine environments. Their persistence is often tied to being halogenated organics, since the bond strength of C to Cl, for instance, is much stronger than C to C. For instance, polychlorinated biphenyls, PCBs, are known to have lifetimes of many hundreds of years in river sediments. How long a detectable signal would persist in ocean sediment is, however, unclear. Other chlorinated compounds may also have the potential for long-term preservation, specifically CFCs and related compounds. While there are natural sources for the most stable compound CF4, there are only anthropogenic sources for C2F6 and SF6, the next most stable compounds. In the atmosphere, their sink via photolytic destruction in the stratosphere limits their lifetimes to a few thousand years. The compounds do dissolve in the oceans and can be used as tracers of ocean circulations, but we're unaware of studies indicating how long these chemicals might survive and or be detectable in ocean sediments, given some limited evidence of microbial degradation in anaerobic environments. Donovan and Strand, 1992. Other classes of synthetic biomarkers may also persist in sediments. For example, steroids, leaf waxes, alkanones, and lipids can be preserved in sediments for many millions of years. What might distinguish naturally occurring biomarkers from synthetics might be the chirality of the molecules. Most total synthesis pathways do not discriminate between D and L chirality, while biological processes are almost exclusively monochiral. For instance, naturally occurring amino acids are all L forms, and almost all sugars are D forms. Synthetic steroids that do not have natural counterparts are also now ubiquitous in water bodies. Chapter 2.5 Plastics. Since 1950, there have been a huge increase in plastics being delivered into the oceans. Although many common forms of plastics such as polyethylene and polypropylene are buoyant in seawater, and even those that are normally heavier than water may be incorporated into flotsam that remains at the surface, it is already clear that mechanical erosional processes will lead to the production of large amounts of plastic, micro and nanoparticles. Surveys have shown increasing amounts of plastic marine litter on the seafloor from coastal areas to deep basins in the Arctic. On beaches, novel aggregates, plastiglomerates have been found where plastic-containing debris comes into contact with high temperatures. The degradation of plastics, mostly by solar ultraviolet radiation and in the oceans, occurs mostly in the photic zone and is notably temperature dependent. Other mechanisms such as thermooxidation or hydrolysis do not readily occur in the ocean. The densification of small plastic particles by fouling organisms, ingestion, and incorporation into organic rains that sink into the seafloor is an effective delivery mechanism to the seafloor, leading to increasing accumulation in ocean sediment where degradation rates are much slower. Once in the sediment, microbial activity is a possible degradation pathway, but rates are sensitive to oxygen availability and suitable microbial communities. As above, the ultimate long-term fate of these plastics in sediments is unclear, but the potential for very long-term persistence and detectability is high. Chapter 2.6 Transuranic Elements. Many radioactive isotopes that are related to anthropogenic fission or nuclear arms have half-lives that are long, but not long enough to be relevant here. However, there are two isotopes that are potentially long-lived enough, specifically plutonium-244, half-life of 80.8 million years, and curium-247, half-life 15 million years, would be detectable for a large fraction of the relevant time period if they were deposited in sufficient quantities, say, as a result of a nuclear weapon exchange. There are no known natural sources of plutonium-244 outside of supernovae. Attempts have been made to detect primordial plutonium-244 on Earth with mixed success, indicating the rate of actinide meteorite accretion is small enough for this to be a valid marker in the event of sufficiently large nuclear exchange. Similarly, curium-247 is present in nuclear fuel waste and as a consequence of nuclear explosion. Anomalous isotopic ratios in elements with long-lived radioactive isotopes are also possible signatures. For example, lower than usual U-235 ratios and the presence of expected daughter products in uranium ores in the Franceville Basin in the Gabon have been traced to naturally occurring nuclear fission in oxygenated hydrated rocks around 2Ga. 2.7 Summary. The Anthropocene layer in ocean sediment will be abrupt and multivariate, consisting of seemingly concurrent specific peaks in multiple geochemical proxies, biomarkers, elemental composition, and mineralogy. It will likely demarcate a clear transition of faunal taxa prior to the event compared to afterwards. Most of the individual markers will not be unique in the context of Earth's history as we demonstrate below, but the combination of tracers may be. However, we speculate that some specific tracers that would be unique, specifically persistent synthetic molecules, plastics, and potentially very long-lived radioactive fallout in the event of nuclear catastrophe. Absent those markers, the uniqueness of the event may well be seen in the multitude of relatively independent fingerprints as opposed to a coherent set of changes associated with a single geophysical cause. Chapter 3. Abrupt Paleozoic, Mesozoic, and Cenozoic events. The summary for the Anthropocene fingerprint above suggests that similarities might be found in geologically abrupt events with multivariate signatures. In this section, we review a partial selection of known events in the Paleo record that have some similarities to the hypothesized eventual anthropogenic signature. The clearest class of events with such similarities are the hypothermals, most notably the Paleocene-Eocene thermal maximum, 56 million years ago. But this also indicates smaller hypothermal events, ocean Anoxic events in the Cretaceous and Jurassic, and significant, if less well-characterized events in the Paleozoic. We don't consider of events such as the K2 extinction event or the Eocene-Oligocene boundary, where there are very clear and distinct causes, asteroid impact combined with massive volcanism, and the onset of Antarctic glaciation, likely linked to the opening of Drake Passage, respectively. There may be more events in the record, but that are not included here simply because they may not have been examined in detail, particularly in the pre-Cenozoic. Chapter 3.1. The Paleocene-Eocene Thermal Maximum, PETM. The existence of an abrupt spike in carbon and oxygen isotopes near the Paleocene-Eocene transition around 56 million years ago was first noted by Kemet and Scott 1991 and demonstrated to be global by Koch et al. 1992. Since then, more detailed and high-resolution analyses on land and in the ocean have revealed a fascinating sequence of events lasting 100 to 200,000 years and involve a rapid input in perhaps less than 5,000 years of exogenous carbon into the system, particularly possibly related to the intrusion of the North American igneous province into organic sediments. Temperatures rose 5 to 7 degrees Celsius, derived from multiple proxies, and there was a negative spike in carbon isotopes and decreased ocean carbon preservation in the upper ocean. There was an increase in kaolinite clay in many sediments, indicating greater erosion, though evidence for a global increase is mixed. During the PETM, 30 to 50% of benthic foraminiferal taxa became extinct, and it marked the time of an important mammalian and lizard expansion across North America. Additionally, many metal abundances, including V, zinc, MO, and Cr, spiked during the event. Eocene events. In the 6 million years following the PETM, there are a number of smaller, though quantitatively similar, hyperthermal events in the record, notably the Eocene Thermal Maximum 2 event, ETM2, and at least 4 other peaks are characterized by significant negative carbon isotope excursions, warming, and relatively high sedimentation rates driven by increases in terragenous input. Arctic conditions during ETM2 show evidence of warming, lower salinity, and greater anoxia. Collectively, these events have been denoted Eocene Layers of Mysterious Origin, ELMO. Around 40 million years ago, another abrupt warming event occurs, the Mid-Eocene Climate Optimum, MECO, again with accompanying carbon isotope anomaly. Chapter 3.3. Cretaceous and Jurassic Ocean Anoxic Events. First identified by Schlanger and Jenkins, 1976, ocean anoxic events, OAE, identified by periods of greatly increased organic carbon deposition and laminated black shale deposits, are times when significant portions of the ocean, either regionally or globally, became depleted in dissolved oxygen, greatly reducing anaerobic bacterial activity. There is partial, though not ubiquitous, evidence during the larger OAEs for euxenia, when the ocean column becomes filled with hydrogen sulfide. There were three major OAEs in the Cretaceous and Weissert event 132 million years ago. OAE 1 around 120 million years ago, lasting about 1 million years. Another OAE 2 around 93 million years ago, lasting around 0.8 million years. At least 4 other minor episodes of organic black shale production are noted in the Cretaceous, but seem to be restricted to the Proto-Atlantic region. At least one similar event occurred in the Jurassic 183 million years ago. The sequence of events during these events have 2 distinct fingerprints, possibly associated with the 2 different theoretical mechanisms for the events. For example, during OAE 1, there is evidence of strong stratification and a stagnant deep ocean, while for OAE 2, the evidence suggests a decrease in stratification, an increased upper ocean productivity, and an expansion of the oxygen minimum zones. At the onset of events, there is often a significant negative excursion, as in the PETM, followed by a positive recovery during the events themselves as the burial of light organic carbon increased and compensated for the initial release. Causes have been linked to the crustal formation, tectonic activity, and enhanced CO2, or possibly CH4 release, causing global warmth. Increased seawater values suggest increased runoff, greater nutrient supply, and consequently higher upper ocean productivity. Possible hiatuses in some OAE 1 sections are suggestive of an upper ocean dissolution event. Other important shifts in geochemical tracers during the OAEs include much lower nitrogen isotope ratios, increase in metal concentrations. Positive shifts in sulfur isotopes are seen in most OAEs, with a curious exception in OAE 1 where the shift is negative. Chapter 3.4 Early Mesozoic and Late Paleozoic Events. Starting from the Devonian period, there have been several major abrupt events registered in terrestrial sections. The sequence of changes and the comprehensiveness of geochemical analyses are less well known than for later events, partly due to the lack of existing ocean sediment, but these have been identified in multiple locations and are presumed to be global in extent. The late Devonian extinction around 380 to 360 million years ago was one of the big 5 mass extinctions. It's associated with black shales and ocean anoxia, stretching from the Kellwasser events to the Hagenberg event at the Devonian Carboniferous boundary around 359 million years ago. In the late Carboniferous, around 305 million years ago, the Pangean tropical rainforest collapsed. This is associated with a shift towards drier and cooler climate and possibly a reduction in atmospheric oxygen, leading to the extinction of some megafauna. Lastly, the Permian extinction event around 252 million years ago lasted about 60,000 years, was accompanied by an initial decrease in carbon isotopes, around 5 to 7%, significant global warming, and extensive deforestation and wildfires associated with widespread ocean anoxia and euxenia. Pre-event spikes in nickel have also been reported. Chapter 4 Discussion and Testable Hypotheses. There are undoubted similarities between previous abrupt events in the geological record and the likely Anthropocene signature in the geological record to come. Negative, abrupt excursions, warmings, and disruptions in the nitrogen cycle are ubiquitous. More complex changes in biota, sedimentation, and mineralogy are also common. Specifically, compared to the hypothesized Anthropocene signature, almost all changes found so far for the PETM are of the same sign and comparable magnitude. Some similarities would be expected if the main effect during any event was a significant global warming, however caused. Furthermore, there is evidence at many of these events that a warming was driven by a massive input of exogenous biogenic carbon, either as CO2 or CH4. At least since the Carboniferous around 300 to 350 million years ago, there have been sufficient fossil carbon to fuel an industrial civilization comparable to our own, and any of these sources could provide the light carbon input. However, in many cases, this input is contemporaneous to significant episodes of tectonic and/or volcanic activity. For instance, the coincidence of crustal formation events with the climate changes suggests that the intrusion of basaltic magmas into the organic-rich shales or petroleum-bearing evaporites may have released large quantities of CO2 or CH4 to the atmosphere. Impacts to warming and/or carbon influx, such as increased runoff, erosion, etc., appear to be qualitatively similar whenever in the geological period they occur. These changes are thus not sufficient evidence for prior industrial civilization. Current changes appear to be significantly faster than the paleoclimatic events, but this may be partly due to limitations of chronology in the geological record. Attempts to time the length of prior events have used constant sedimentation estimates or constant flux markers, or orbital chronologies, or supposed animal or seasonal banding in the sediments. The accuracy of these methods suffer when there are large changes in sedimentation or hiatuses across these events, which is common, or rely on the imperfect identification of regularities with specific astronomical features. Additionally, bioturbation will often smooth an abrupt event, even in a perfectly preserved sedimentary setting. Thus, the ability to detect an event onset of a few centuries or less in the record is questionable, and so direct isolation of an industrial cause based only on apparent timing is also not conclusive. The specific markers of human industrial activity discussed above, plastics, synthetic pollutants, increased medical concentrations, etc., are, however, a consequence of the specific path human society and technology has taken, and the generality of that pathway for other industrial species is totally unknown. Large-scale energy harnessing is potentially a more universal indicator, and given the large energy density in carbon-based fossil fuel, one might postulate that a light sea signal might be a common signal. Conceivably, solar, hydro, or geothermal energy sources could have been tapped preferentially, and that would greatly reduce any geological footprint, as it would ours. However, any large release of biogenic carbon, whether from methane hydrate pools or volcanic intrusions into the organic-rich sediments, would have a similar signal. We therefore have a situation where the known unique markers might not be indicative, while the perhaps more expected markers are not sufficient. We are aware that raising the possibility of a prior industrial civilization as a driver for events in the geological record might lead to rather unconstrained speculation. One would be able to fit any observation to an imagined civilization in ways that would basically be unfalsifiable. Thus, care must be taken not to postulate such a cause until actual proven evidence is available. The Silurian hypothesis cannot be regarded as likely merely because no other valid idea presents itself. We nonetheless find the above analyses intriguing enough to motivate some additional research. Firstly, despite copious existing work on the likely Anthropocene signature, we recommend further synthesis and study on the persistence of uniquely industrial byproducts in ocean sediment environments. Are there other classes of compounds that will leave unique traces in the sediment geochemistry on multi-million-year timescales? In particular, will the byproducts of common plastics or organic long-chain synthetics be detectable? Secondly, and this is indeed more speculative, we propose that a deeper exploration of elemental and compositional anomalies in extant sediments spanning previous events be performed, although we expect that far more information has been obtained about these sections than has been referenced here. Oddities in these sections have been looked for previously as potential signatures of impact events, ranging from iridium layers, shocked quartz, microtectites, magnetites, etc. But it may be that a new search and new analysis with the Silurian hypothesis in mind might reveal more. Anomalous behavior in the past might be more clearly detectable in proxies normalized by weathering fluxes or other constant fluxes proxies in order to highlight times when productivity or metal production might have been artificially enhanced. Thirdly, should any unexplained anomalies be found, the question of where there are candidate species in the fossil record may become more relevant, as my questions about their ultimate fate. An intriguing hypothesis presents itself should any of the initial releases of light carbon described above be related to prior industrial civilizations. As discussed in section 3.3, these releases often triggered episodes of ocean anoxia via increased nutrient supply, causing a massive burial of organic matter, which eventually became source strata for further fossil fuels. Thus, the prior industrial activity would have actually given rise to the potential for future industry via their own demise. Large-scale anoxia, in effect, might provide self-limiting but self-perpetuating feedback of industry on the planet. Alternatively, it may be just a part of a long-term episodic natural carbon cycle feedback on a tectonically active planet. Perhaps unusually, the authors of this paper are not convinced of the correctness of their proposed hypothesis. Were it to be true, it would have profound implications, and not just for astrobiology. However, most readers do not need to be told that it is always a bad idea to decide on the truth or falsity of an idea based on the consequences of it being true. While we strongly doubt that any previous industrial civilization existed before our own, asking the question in a formal way, what articulates explicitly what evidence for such a civilization might look like, raises its own useful questions related both to astrobiology and to Anthropocene studies. Thus, we hope that this paper will serve as a motivation to improve the constraints on the hypotheses so that in future we may be better placed to answer our own title question.